Hello everybody and welcome to a new cool video of our machine learning course. And in this video we're going to see a very beautiful example of using logistic regression in R to predict the direction of the stock market, whether it's going up or down, using the data from previous days. So we're going to have, first of all, we're going to use a library called ISLR, which is I think a pre-built library in R. So you just need to call this function to download the data, and inside this library there is like many data sets. The one we're going to use is S-market, called S-market, stands for stock market. So this data consists of percentage returns for the stock market index over 1 to 250 days from 2001 until 2005. So we have all this data. We can use it to train a model, a logistic regression model, to see whether our market is going up or down, so 0 or 1. Let's first call the library. This is just a warning, you can ignore it. And I think we used this function last time, but we didn't use that one. So this function is just like for giving us the names of each row that we're going to use. And the second function, I'm going to show you what does it do. So the first function gave us the names. So we have the year, this is for day 1, day 2, 3, 4, 5, volume, and today, and the direction. This is going to be, of course, I think you already guessed it, this is our y, the direction, because that's what we want to predict. The function attach, what does it do is, you know that, for example, if we want to use year, we have to use, like, we have to like write S market. We have to write S market, then dollar, then year. We have to do that all the time. But since we did attach now, that means we can just write year without any S market and dollar signs to get the year. You see, we got the years. So we have the years from 2001 until 2005. So this is all our years data. Great. So now how to create our model. You know, like comparing to Python, R is super easy, super simple. Last time we used the LM, which just stands for linear model. This is now we're gonna use GLM, which is a generalized linear model, but we need to specify family equals binomial. You can guess by, like from the word by, you can guess what does it mean. That means we're gonna have two classes to predict. So the family is binomial, and this is actually stands for binomial families in algebra. So this has something to do with mathematics, but we are not caring about mathematics that much. We are caring about applying what like machine learning and moving forward without any complications. We're gonna use the binomial family. We're gonna use the data from S-market that we just download from here, and this is the direction. This is our y that we're gonna predict. This is our x's, the percentage in day 1, day 2, 3, 4, 5, and the volume. This is our x's. So we have 6 x's, 6 features, and 1 label. Using GLM, how do we know it's logistic regression? Because we specified family equals binomial. So let's fit this model to the data. Done. It's that fast. Let's see the summary. We already showed you the summary last time, the summary function. So here we have our data. This is the W, the parameters. This is the bias. This is the bias intercept in R. This is the bias, and this is the parameters with each x we have. So we have 6 x's, and that's how we predict our model. You must remember this because it is super important. Last time I told you that the lowest value that we have is the one that the lowest value with the lowest p value means like this feature is more important. But as you see here, like last time we had like 0.000, maybe 12 zeros, 1, like super low. But you notice here that it's not that low. It's low, but not that low, especially these 3 or 4 values. So what's the reason for that? Like predicting stock market is really hard, like even for experts. So you can like guess. You can guess that like it's hard even for our models to even like you can guess like if someone can predict like with 90% accuracy predict like the stock market, he's gonna be like super rich. So yeah, because it's really hard to predict. It's also like the p-value is kind of high comparing to like previous time we had, and we're gonna see even more of that, so don't worry. But put it in mind, like the lowest p-value, the best. So if someone asks, okay, which like feature is more important to predict, of course you're gonna see 1. What does that mean? Is last day. That means if I want to predict the direction of the stock market, it's better to see last day, yesterday, and the day before that. Before that, it's harder to tell. Like it's way harder. So yeah, let's see more. So as I told you, the smallest p-value here is associated with lag 1, which is the yesterday. This is yesterday. It means yesterday. I didn't tell you about that. Negative and positive coefficients. So you can see that here it's negative. These two are negative, and the rest are positive. So what does that mean? Like we have to interpret that, and that's the important part in our modeling, because we want to interpret the results. So yesterday, this is yesterday, and this is the day before that. We have negative slope. What does that mean? That means if yesterday the stock market went up, like up, all the prices went up. Today, we should predict that the market is going down. Like 0.07 is really low, but mostly it's going down because yesterday it went up. And if it goes down yesterday, that means today there is a more probability that it's going up because it went down yesterday. So that means if it's minus, that means it's opposite to the data before, like opposite to yesterday. And that's how we interpret a minus, a negative estimation. So yesterday it went up, today there is a higher chance that it goes down, and so on. So it's always the opposite because it's minus. If it's positive, that means it's with it. Anyway, so let's calculate the prediction for training data. And when I say training data, if you remember last video in in Python, we splitted the data. We didn't split it yet, but we are going to do that later. Anyway, So we want to calculate predictions for the training data. But how we do that? Because like here you can see we didn't provide any data for prediction. We used that function last time. I hope you remember how we used it last time. Like you give it the model, you give it the data and the type, and that's it. But this time if you don't give any data for the predict function, it just uses the training data automatically. That's great about R. Like everything is automatic. You don't have to worry about it. If you don't put the data here, it's going to use the training data, the data that we used it to fit the model. So it's going to give us what? The training results. Like we can calculate from there the training error. Okay, so we calculate the probabilities for training data. How we know it's training data? Because we didn't provide any data. It automatically gets the training data. So let me show you the first 10 calculated probabilities. Of course, we have way more than 10, but let's see just the first 10. So 0.5, 0.48, 0. How to interpret these probabilities? As I showed you in the theoretical course, the theoretical part of the course, if it's more or equal 0.5, it's 1. If it's less, it's 0. So it's 1, 0, 0, 1, 1, 1, 0, 1, 1, 0. But what does 1 mean and what does 0 mean? I mean, which one is up and which one is down? We want to predict up or down, but we didn't provide which one is 1 and which one is 0. How do we know that? We can see the contrasts that was provided by R, because R creates automatically his own interpretation. So we can see it by that, and you can see here that down means 0 and up is 1. So this is 1, this is going up, down, 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 up, 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 down, up, and down. So now we know that. Let's try to show it as up and down better than show it in numbers like that. So let's first create a long vector of 100 and 1250. How did I know that it's 1250? Simply just create see how long the dimension dim of directions. Oh, I made a mistake. We don't use this function. But anyway, just see just write dimension. You can see here. So yeah. So 1200. This is 1247, 48, 49, and 50. So 1250. That's how I knew it's 1250. We initialize. This is like creating a long vector. We initialize with all downs. The vector is all downs. Then what we do is we take our probabilities. Whenever we find that the probability is way more it's totally more than when we found the probability is totally more than 0.5, 0.5, we initialized by up. That means this is a Boolean. If it's true, if this is true, we put up in the predictions. We change the down and we put it up. And that's how we change all the ones that are more than 0.5 with up and leave the others as down. And that's how we do it. So if we put dot, and you can see like ups and downs, predictions for our model. But now we just have ups and downs, but we don't know like the accuracy of our model. That's our goal. Accuracy is also how many times our model was right and how many times was wrong. So we create a table that have the predictions as rows and the direction that means the actual direction, like the real direction, as columns, and that's how we compare between them. So here is the table. This is our predictions and this is the real directions. So down was predicted 145 times, but it was up 141 times. It was down. It was like really down. Our direction was down and the prediction was down. So that's like 0.501, maybe 51. I'm not sure. We're gonna calculate that. And when our model says up and the direction says up, it was 507 times out of all of these, this plus this. So most of the time we can say that most of the time our model is right, but not really like with a big margin. Not really with a big margin. So let's see the mean. What do we mean by that? That's like the average when our predictions were exactly as labels. That means when our model was right. So this is the accuracy, the training accuracy of our model, 52.16%. That's the training accuracy of our model, and that's the optimistic accuracy because we said that training of accuracy is usually optimistic. You can see, like, you can feel how much is like really hard to predict a stock market, and that's why it's like really huge market for AI researchers to work on. So, but the most important question is, what is the test error rate? That's like we have the training error rate, but like the most important question, we want the tests. So let's do like we did in Python. Split the data into training and test data, and then create a vector corresponding to the observations from 2001 to 2004. So we use the data from 2001 to 2004 as our training data, and the data from 2005 as our test data. So our training data is going to be all the data where the year is less than 2005, before 2005. And the data of 2005 is going to be the data of stock market where it's not equal to train. That means all the data before 2005. This is the negation. This is the negation of this. Okay. So let's take the labels, which are the directions of the stock market, and this is taking the labels of all the test data. and I called it direction 2005 because it's the directions of the year 2005 test data. Now we have the x's, the features, and we have the directions. So now how do we like use the subset? Easy. We just uh, define here, like we add another parameter to the GLM function called subset. That means we're gonna use this subset for train. So this is like one of the great things and the easiest things about R. It's always like providing really easy solutions for our problems. So you just define one parameter subset equals train, and that's it. And you just specify like which subset, and that's it. It uses that subset for the training. So here the direction, all the days, the volume, the data, and of course the family. This is to specify that it's logistic regression, and the subset that we're gonna use for training to fit the data. And of course the rest of the data, like other than this subset, is going to be for testing. So yeah. So we create our model. We fit, you can say also we fit our data to the model. Now let's calculate the probabilities. That means predict using what? The test data, not the training data. You remember here we used the same as the test data. How we know? Because we didn't specify any data. But now we are going to use the test data, not the training data. Here it was the training data. Great. Now let's calculate the accuracy exactly like we did here by creating a vector. How we know that it's 252? Simply because the predictions, or as you can say, the probabilities we have is, we don't have the number, but anyway, the the probabilities we have are 252, and we initialize it all with down. Then we create like a Boolean expression, that means true or false. If it's true, initialize it by up. If it's not, just leave it as down. Then create a table to see our predictions. Let me show you here. Here's the table. This is 77 times our model, and the real direction was were like equal, and 97 times were not equal. That means 97 times our model was wrong and 77 times was right. That means it's less than 50%. Then up, it was 44 times right and 34 times wrong. That means the up times were actually better than the down times. And let us see the mean. This is the mean to calculate when they were like equal. That means right when our model was right, and the mean when our model was wrong. Let's see both of them. When our model was right and when our model was wrong. Is there a mistake? Oh, Okay, so 48% of the time our model was right. 51% of the time, you can say 52% of the time, our model was wrong. So our model is bad. Like most of the time, our model is wrong. Do you think there is a way to improve it? Like, I'm gonna give you just a second. You can pause the video if you want. Do you think that we can improve our model, and how? That's I want you to have like this critical thinking, and just remember what I told you all like since we started the course. Okay, I'm gonna answer for that. Yes, we can do it. How? You remember? Let me show you the summary of. So this is the summary of our model. You remember when I told you that how to improve the model is just like sometimes you are adding too much many like many more than you need features. For here we are adding many features, and how do you indicate that these features are important or not? Just by looking to the p-value here. So you can see that, of course I'm not talking about the bias because the bias is automatically calculated, but the features here you choose them. So you can see this is 0.2, 0.3, 0.8, and 0.9, 0.9, 0.6. So this is like super high features. There is a high chance that we don't need these features. So what we do, how to improve this model? Just delete these features. And that's the critical thinking. Just like the p-value is too high, like I don't need them. So you just delete them. So in my opinion, using just yesterday and the day before that to predict today's direction of the market is all we need. So let's do that. Let's just take okay, fit this data. Let me show you. Just fit the data, okay, without using. We just use yesterday and the day before it, and that's what we want. This is our new model, just with yesterday and the day before that. Why? Because the p-value of these 2 days are the lowest. You can see, and the others are super high. Usually more than 0.5, just give up on it. Let's calculate the probabilities. And now, you see the surprising results? You can see here that 35 times our model was right and 35 times was wrong. We are using the same test data. That means it's like the same data, the same input, just the model training. We trained the model on just yesterday and the day before that, not all the weekdays. So 35, actually it was way worse last time. It was 77 to 97, that like 0.48 accuracy, and now we are having 0.56 accuracy. So 56 accuracy, that's really good, like comparing to last time. And the times when our model was wrong is just like 44% of the time. So this model is way better than the previous model just by taking down the the features that have high p-value, or aka features that we don't need. I hope you understand this really well. If you didn't, just repeat the video again. It's really important to know that the idea is really easy. Okay, you have high p-value, just delete this feature. It's not useful for you. It's useless. And so on. So that was our so the question, the answer for this, that is yes, and I will leave it for you to do it again. Thank you very much. That was like really nice video. I hope you learned a lot. There was like a lot of things we learned. I think the video is longer than usual, but anyway, thank you very much, and see you next video.